Good evening, everybody. So, in the previous lecture, we discussed about the dynamic similarity and mentioned that the dynamic similarity is similarity of forces. Six forces we have considered, and these six forces at the corresponding points, the ratios should be equal, not only in magnitude, the direction in the prototype and model also, it should be in the same direction. Then, actually, to simplify that, the ratios of forces we have taken through the dimensionless numbers. These dimensionless numbers are nothing but they're all ratios of forces. So that's what we have shown in the last, what you call it as lectures. Then what we will do with these dimensionless numbers, why we have done that exercise, what is the significance of these numbers, and then based on these numbers, what are the modal laws that are defined, and each modal law is applicable under what circumstances, which is the model law which is used for a particular problem, that all that we will start discussing it in today's and the consequent next lectures we discuss on that. Let me straight away go into the first thing, the next, what is the use of this the dimensionless numbers, and then basically from the dimensionless numbers we will go into the model laws. In the previous lecture, we mentioned that the dynamic similarity between the model and prototype exists if the ratios of forces acting on the model and prototype basically are same. When we are considering these forces, kindly note that the ratios of forces at the corresponding points in model and prototype are same. Further, force being vector quantity, not only the magnitude, not only the ratios of magnitude of forces is same, but also the direction should be same. Now, if we take note that whatever the dimensionless numbers we have taken, for example, first one, if I write the forces, inertia force is the first one. Then after the inertia force, next one is we mentioned viscous force. Then next one we have mentioned it as a gravity force. The next one is pressure force. Then after the pressure force, we have taken surface tension force. And last one is elastic force, which is also compressibility force. So these are the six forces. Now, if I take the ratio between these two, then we got one dimensionless number, Reynolds number. If we take the ratio between these two under square root, of course, this is under square root, then we call this number as Froude number. If we take basically these two, again square root, we call that number as Euler number. If we take these two, again square root, this is Weber number. And if we take this two, the last top and bottom, it's again square root, Mach number. So first one is Reynolds number, second one is Froude's number, third one is basically Euler number, next one is Weber number, last one is Mach number. So these are the dimensionless numbers, which is 1, basically 2, 3, 4, 5. Now, if you see, all these numbers are nothing but they're all the ratios of the forces actually. So now what I can write, the ratios of forces are the dimensionless numbers. Are the dimensional numbers. So that means it means for dynamic similarity, for, for dynamic similarity between the model and the prototype, these dimensionless numbers, these dimensionless numbers should be same for the model and prototype. But it is very difficult that basically that all these numbers, all these dimensionless numbers should be same. It is very difficult to basically to satisfy. It is very difficult to satisfy that all these dimensionless numbers should be same. So that is why, based on the problem, we identify which forces are predominant and then that dimensionless number shall be satisfied, that shall be used in satisfying dynamic similarity. So the meaning is, instead of taking all the forces, which are now the forces being converted into dimensionless numbers, all the dimensionless numbers we will not consider. In a particular problem, which are the forces that are dominant? Suppose, for example, in a problem, the inertia force and viscous forces are dominant. Then we use the dimensionless number, Reynolds number. And other dimensionless numbers we will not touch at all. Similarly, we take in a particular problem, the Froude number is what you call it as the other, that means the gravity force is important. When the gravity force is important, the Froude number will come into picture. Suppose in other problem pressure forces are important, then actually the Euler's number will come into picture. If suppose in a particular problem what you call it a surface tension force is important or significant, then Weber number will come into picture. So all the other numbers will not be considered. Only if naturally, if the model and prototype, the ratios when we are calculating it, if this particular number is satisfied, we take it granted that dynamic similarity exists between the model and prototype. So this is the first thing actually which we should understand. So now basically based on these numbers, the modal laws are being defined. Modal laws are defined based on these numbers only. So this is the, or these modal laws are also called as similarity laws, right? What are these modal laws actually? So based on these numbers only, these are, number one is Reynolds modal law. The second one is Froude modal law. Third one is then Euler's modal law. Then fourth one is Weber modal law. Last one is Mach modal law. So different modal laws based on these numbers are defined. So now let us take only the first modal law in this class. So what is Reynolds modal law? Reynolds model law says that, right, the Reynolds number for the model is equal to Reynolds number for the prototype. That's all. Reynolds number for the model is equal to Reynolds number for the prototype. What is Reynolds number for the model? It is rho V L by mu for the model is equal to rho V L by mu for the prototype. In other words, if I write rho m Vm Lm by mu m is equal to rho p Vp Lp by mu p. Or if we make it actually in terms of ratios, if I take it, then it will become rho r Vr Lr by mu r is equal to 1. So this is the Reynolds model. This is the first one. So what is the use of this Reynolds model law? So in the Reynolds model, what are the forces that are there? Inertia force mass into acceleration, whereas the viscous force it is shear stress into area. So wherever viscous forces are dominant, this law is applicable. Now next, where generally practically where we come across such type of applications, pipe flow. This is one basically flow through pipes. If you take it, there actually the type of flow, whether it is laminar or turbulent, all this is based on basically the viscous forces are dominant there. So that is why one example for Reynolds model law is pipe flow. The second one is basically the submerged bodies. Any submerged body, if you take it, then Reynolds model law is applicable. What are the examples? For example, submarine. Submarine is completely submerged in seawater. So wherever the submarine cases are there, submarine manufacturing thing is there. Now we try to get the dynamic similarity or satisfy the dynamic similarity using Reynolds model law. Second one is aircraft. Aircraft is also completely submerged in air. So these are the two things actually. So where generally we apply, we use the Reynolds model is wherever the pipe flow problems are there, and at the same time wherever the body is completely is submerged in the fluid. Such type of cases also we will take it up. Please note that. So any problem that comes under Reynolds model law is basically based on these two. So now if you see in the exam also any pipe flow problem that you encounter, automatically you should understand that it is the case of a Reynolds model law. The dynamic similarity can be satisfied using Reynolds model law. Similarly, if you see a problem like, for example, a submarine or aircraft problem, such type of thing, then immediately it is a case of a submerged body, then naturally we have to use Reynolds model law for this solving this problem. Now I will show you one or two problems based on this particular thing, particular model law. So based on Reynolds model law, if I take it, one of the problems, number of problems only related to pipe flow, submerged bodies. Suppose if you take it, water is flowing through a pipe of diameter 30 centimeters at a velocity of 4 meters per second. Find the velocity of oil flowing in another pipe of diameter 10 centimeters. If the dynamic similarity is satisfied between the two pipes, the viscosity of mu water is equal to 0.01 poise, mu oil is equal to 0.25 poise. Specific gravity of oil is zero point 0.8. Water is flowing through a pipe of diameter 30 centimeters at a velocity of 4 meters per second. Right. Find the velocity of oil flowing through a pipe of diameter 10 centimeters if the dynamic similarity exists between the thing. Suppose now let us take it. First one, pipe 1, if I take it. What are the things he has given? Diameter d is equal to, for example, you call it as d is equal to 30 centimeters. What is the other one? Velocity is equal to 4 meters per second. So this also 0.3 meters. Then what is the other one? Pipe 1, what is flowing through pipe 1? Water. So mu water is equal to zero point zero 0.01 boys. This is next. So it is equal to 0.001 Newton second per meter square. Right. Then afterwards, what is the specific gravity of water actually? Specific gravity of water is equal to specific gravity is equal to, because here you write water so that it will be very easy, is equal to 1. So therefore, how rho, basically rho water is equal to, naturally it will be 1000 kg per meter cube. So all this is regarding pipe 1. Now let me take pipe 2. So water flowing, the liquid flowing through it is oil. That is first thing. So what the data has given? Diameter he has given 10 centimeters, zero point 0.1 meters. He asked what is velocity. That is the question. Then he has given mu oil is equal to 0.25 poise is equal to 0.025 Newton second per meter square. Then rest one is specific gravity. He has given it as it is equal to zero point 0.8. So therefore, basically rho oil is equal to zero point 0.8 into 1000. So it is 800 kg per meter cube. So this is over. So now if I take it basically, so what according to Reynolds model law, what is the Reynolds number for this here is equal to Reynolds number for this. Because it is a pipe pro problem, Reynolds model law is used. Reynolds model law is used basically, right? So then in that case, what is Reynolds model? Reynolds number here? It is when it is pipe, the characteristic length L is equal to the diameter already I mentioned in the previous lecture. So that means rho V d by mu for the pipe 1 is equal to, here rho 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 V d by mu per pipe, right? Both should be, what I should do, both should be equal. So now I will take it. For example, first pipe, if I take it, what is rho 1000 into what is velocity 4 into what is diameter zero point 0.3 divided by what is mu he has given, mu is equal to basically 0.001. So this is here is equal to, on this side what is here, rho is 800, v is not known, diameter is 10 centimeters, divided by mu is equal to 0.025, right? This is the, so equating both the things, if we find out what is v, straight away it comes to 37.5 meters per second. So this is one important problem regarding pipe. Similarly, we can really solve another problem in the case of a submarine also, because that is the general thing that will be used here. Now take the problem of a submarine. the ratio of lengths of a submarine and its model is 30 is to 1. Next. The speed of the submarine is 10 meters per second. The model is to be tested in a wind tunnel. Find the speed of the air in the wind tunnel. Also determine the ratio of drag between the model and prototype. Take kinematic viscosity for seawater is equal to 0.012 Stokes and for air as 0.016 Stokes. Similarly, rho for seawater is equal to 1030 kg per meter cube and rho for air is equal to 1.24 kg per meter cube. So now our objective in this problem is to prepare the model of a submarine first. And if you want to test the model of the submarine, then naturally what is the speed of air in the wind tunnel where the model is tested actually, and determine the ratio of drag. So first thing I want to make it clear, drag is nothing but actually drag means resistance force. Resistance, right? Now there are two things. Here it is prototype, the original one. Always like this, you should write the model. These are the two. So when I take it prototype, and prototype is basically the original one was tested in seawater, whereas model is tested in wind tunnel, that is the fluid there is air. So this is the second one which you should understand, right? Text. Afterwards, what are the other data that he has given? Let us write it. For example, velocity of the prototype. He has given it as 10 meters per second. Right? That is one data he has given. Then second one, he has given the rho for the seawater. That means for the prototype related thing. What is he has given? 1030 kg per meter cube. Similarly, nu is kinematic viscosity. For the seawater, he has given it as how much actually? 0.012 Stokes, right? So 0.012 into 10 to the power of, if I convert it also, it is equal to 0.012 into 10 to the power of minus 4 meters square per second. So this is what the prototype data. So what he has asked, what is the velocity here? That we don't know. That is what he has asked. Then basically what is he has given, rho m is equal to, this is air, 1.24 kg per meter cube, right? Then similarly, new model is equal to point 0.016 stokes. It is equal to 0.016 into 10 to the power of minus 4 meter square per second. And one more data he has given is the length of prototype. Length of, I'm writing it in the middle, this you see it. Length of prototype divided by length of model is equal to 30 by 1. So 30. This is what LR he has given. So this is also he has given. So now naturally when the moment it is a submerged body, we apply Reynolds model law. What Reynolds model law speaks to us, it is Reynolds number for the prototype for the model is equal to Reynolds number for the prototype. That means Reynolds number for the model means rho m v m, right? L m divided by mu m is equal to rho, basically p v p L p divided by u p. But he has not given dynamic viscosity. So the same thing can be written as V m L m by mu m by rho m is equal to Vp Lp by mu p by rho p. So this is nothing but actually kinematic viscosity, and this is nothing but actually kinematic viscosity. So now I can express Reynolds model law as Vm Lm by nu m is equal to Vp Lp by nu. So now already we m is which we don't know into, then lm, they have not given lm but they have given lp. So if now suppose for example, now what, how I will solve, so what I want already I am clear, vm is equal to, if I take this also on the other side, so vp LP into nu M divided by nu P into LM, or it is equal to, see please, VP into LP by LM, right? This also I will bring it out the, or I will put the same, doesn't matter. Yes. So now I know actually what is VP is equal to, VP he has given it as how much he has given, VP is equal to 10. 10 into LP by LM is nothing but 30 he has given into nu m by nu p means what is nu m actually? Nu m means the kinematic viscosity, 0.016 into 10 to the power of minus 4 divided by point, basically 0.12 into 10 to the power of minus 4. If we calculate this actually, then we are going to get this 400 meters per second. This is the first answer, right? Now let us go into the second. Second, what is what he asked? Ratio of drag. I already mentioned drag means ratio of forces in model and prototype. So I take it Fp divided by Fm is equal to, the drag force is nothing but mass into acceleration. So that we can write rho L square, rho P L P rho L square V square. This is all what we have shown. Inertia, the force is equal to mass into acceleration. Already number of times I have shown. If you want once again, this force is equal to mass into acceleration. So mass is equal to rho L cube into acceleration is equal to, basically we can write it as V by T. So rho L square into L by T into V. So it is nothing but rho L square into L by T is also equal to V, so V square. So finally it is rho L square V square. That's what I have written. Right now, basically, let us take it. You already know what is rho p by rho m. We know it already. LP by LM also we know it. VP by VM also we know it. Let me substitute what is basically the rho p by rho m. The seawater and air they have given. One is 1030 divided by 1.24. This is first one is into LP by LM is already known. It is 30 square into basically VP is equal to, just now VP is given it as 10, and what is VM is equal to 400, which we got. This is also square. So therefore FP by FM is equal to, if you calculate this ratio, you're going to get 467.22. So this is the second problem. So now once again I wish to tell you all that we have two types of problems in the based on Reynolds model law. One is basically pipe flow problem, and the second one is based on the what you call it as submerged bodies. The submerged bodies can be basically in normally the submarine will be one of the most favorite question, where or otherwise aircraft is also one of the question. Suppose now you also can ask me, sir, you are taking submarine. Can we take it the ship also? Please wait for some more time. Wait till the next class. The ship problem. Ship is not a fully submerged body. Ship is only partially submerged body. For partially submerged bodies, in addition to the viscous force, there is one more force which is dominant. That force is basically the what we call it as the gravity force. That also we have to take into account. So that's why for ships directly you cannot use Reynolds model law alone. So only submerged bodies only you can use Reynolds model law. So with this, basically we will stop the lecture at this stage. So in today's class, mainly what is the use of dimensionless numbers, how we really reduced the problem of dynamic similarity satisfying the norm, how we did it. So the dynamic similarity is satisfied based on the dimensionless numbers. Are we using all the dimensionless numbers? No, we are using only whichever dimensionless number is predominant in a particular problem, that only we will take it. So that's why how we have solved the problem, and we have first completed one model law in this lecture. Thank you. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.